Hello, and welcome back to Lecture 17. In this second part of the lecture, we're just going to have a short video where I show you two more examples of double-slit interference. Okay, and I want to clarify one thing. I said that I might have an example where I highlighted a time that we can't really use small angle approximation. I ended up actually removing that example from the lecture notes, so it's not going to be a big focus of this lecture. Again, if it does show up, it would show up in the post-quiz. Okay, so example 3 deals with a very different type of light than the types of light we've been talking about, namely visible light, and that's radio waves, because of course that is a form of very long wavelength light, low frequency or lower frequency, low energy it turns out as well. All right, so two radio antennas are 16 kilometers apart on a north-south axis on high mountaintops. And notice I've already have the solution in here. We're just going to go over I'm going to narrate the solution. So anyway, so they're some distance apart. That's our D. We use this, right? So there's some distance apart. We're told it's 16 kilometers. Okay, so the antennas broadcast identical AM radio signals in phase at a frequency of 4.7 megahertz. Okay. Oh, sorry, I didn't realize my mic was so loud. There we go. So 4.7 megahertz. A freight ship 300 kilometers offshore travels towards the north at 15 kilometers per hour and passes east of the antennas. Okay. So the idea then is that, off to the right, so that would be in the east direction, we have our ship shown in the figure that I've included, and our L is the 300 kilometers, right? That's the offshore distance. Okay, the V is 15 kilometers per hour. That's the velocity. That's going to come up because essentially the idea of giving a velocity is that then I can ask for a time, because we're going to be able to find the distance between bright spots. And then we can find, since we have a constant velocity, that means that the ship is going to be traveling from one bright spot to a next at that constant velocity. Thus, there's going to be a time to go from one bright spot to a next. But you might be wondering, what does a bright spot mean for radio antenna? Well, I bet you can guess, and we're going to see. Okay, so then continuing on, a radio on board the ship is tuned to the broadcast frequency, the one from those towers, and the reception of the radio signal on the ship is at a maximum at a given instant. Okay, how much later until the next occurrence of maximum reception? That's it. A bright spot in terms of radio signals is a maximum reception point. Okay, that's where you get a nice clear signal, as opposed to a case where the radio waves would be canceling each other out and you get no signal at all, actually. Okay, so this is effectively a double-slit interference problem. Okay, with d sine theta equals m lambda for maxima, and since we can assume small theta, we can use our sine theta equals x over L. Okay, and that's just using the fact that tangent of theta is just x over L. Okay, our D is our 10 kilometers. Let's see, that's our spacing of the radio antenna. That should actually be 6. Must have changed the values, so I'll change that to a 6. Okay, let's see here. Let's do it. Looks like this is an image or something, so I gotta write over it with the 6. Okay, so we'll do that. Okay, so 16 kilometers. I'll fix the values as well. Our L is still 300. That's correct. Okay. And we have m equals 1. Why 1? Well, because it turns out if we're going to find the distance between any two bright spots, that's the equivalent of the distance from the central bright spot to the first bright spot. Because all the bright spots, in this case maximum reception locations, are equally spaced. So the distance between any two bright spots is equivalent to an m of 1. Right? That's a good thing to note. Right? Because a lot of problems will ask for spacing between bright spots, and that's the idea of just taking a one integer step. Okay, and then we're going to go ahead and find the wavelength of our light. Okay, so our light, we're told, has a frequency of 4.7 megahertz. If we take the speed of light and divide it by that frequency, and we end up with 63.8. I'm just going to confirm that on the calculator to make sure I didn't change any of those values. So I'll take the speed of light, 3 times 10 to the 8 meters per second, and divide it by our frequency of 4.7 megahertz, which is just 4.7 times 10 to the 6. Okay, so I got 3 times 10 to the 8, divided by 4.7 times 10 to the 6, and I sure enough get 63.8 meters. Okay, so that's as far as radio waves go, that's long for a radio wave because we're talking about AM, and AM waves are much longer than FM waves. All right, so then we've got the idea that I want to find the distance x. Okay, that's what we normally refer to as y. Okay, but here I just call it x for whatever reason, but it's clearly shown here in the figure. And x is then going to be equal to lambda L over d, because that's just y equals lambda L over d, right? That's the familiar formula from back from the key formulas page. Okay, well, since we're traveling at constant velocity, x is equal to just velocity times time. And so then we can just solve for the time as lambda L over d times v. Okay, and the key thing there is that m equals 1, which is why it doesn't show up in the formula. Okay, so then all we have to do is just correct the whole 10 to 16 business. So let me do that here. I'm just going to change the 10 to 16 kilometers. I think I've changed it to 16 because that worked better for making the small angle approximation. It turned out that 10 was pushing it a little bit. I think we were getting an angle of like 20 degrees or something, and that wasn't good because it was not meeting the criteria to make the appropriate approximation. Although I don't know if I ever checked the percent error. All right, so I'm doing 63.8, the wavelength times the distance L, which we usually call R, right? That's the distance from the slits to the screen. Okay, and then dividing by d times v, so divided by 16 times 10 to the 3, just 16 kilometers, or 16,000 meters, and then multiply by the velocity. And the velocity we're told is 15 kilometers an hour, which is just, you can see here, I convert over the kilometers to meters and then divide by 3,600 seconds, which is just the number of seconds in an hour. Okay, so times 15 times 10 to the 3. So I didn't change that. The only thing I changed was the distance between the antenna. All right, so 287 seconds with the new corrected distance. Okay, so let's fix that. Shouldn't be 460, but it should be 287. All right, how many minutes is that? Divide by 60. Let's see. That's 4.8 minutes. All right. So 287 seconds. Okay. Well, technically I was only working with 2 sig figs, so let's make it 290 seconds. There we go. Well, looks good. All right, so hopefully that makes sense. And we can, basically the idea there is that we can do everything with visible light that we do with visible light with something like radio waves as well. Okay, so the last example I want to show you is this one here. Light with a wavelength of 400, and that's example 5, 450 nanometers is shown through a double slit with a spacing of 90 micrometers that is attached to the side of a tank 55 centimeters across. Okay. All right, so then working with that, the tank has a length of 1.24 meters and a screen that runs that length. If a clear liquid is poured into the tank with index of refraction of n equals 1.73, then how many more bright fringes will become visible on the screen as compared to when air filled the tank? Okay, so the whole idea here is first we'll do it with air, okay? So with air, let's find out, how many fringes are going to fit? How many bright spots? Well, first of all, let's find the spacing between bright spots. So we'll call this Maxima Spacing. Yeah, sure, right? And by Maxima Spacing, I mean bright spot spacing. So Maxima Spacing is just going to be equal to y sub m, okay? That's between any two bright spots because they're all, again, all equally spaced. And that's just going to be just r m lambda over d, but of course here m is 1, so then we can just rewrite that as just r lambda over d, okay? So then in this case, since it's air, the lambda will be the one that's given, the 450 nanometers, so then we'd have a spacing of 1.24 meters, and then times lambda over d. Okay, so 450 times 10 to the negative 9 meters divided by our d of 90 times 10 to the negative 6 meters. So 90 times 10 to the negative 6 meters. Okay, and that gives us a spacing of, let's see, so 1.24 times 450 times 10 to the negative 9 divided by 90 times 10 to the negative 6. Okay, so basically 6.2 millimeters, or 6.2 times 10 to the negative 3 meters, right? So that's how close the bright spots are to each other, right? So they're actually quite densely packed, right? Only 6 millimeters apart, like about a half a centimeter. So they would appear like a lot, like a band of really like tightly packed bright spots. It'd still be visible to the naked eye, but they again closely spaced. Okay. I think a good thing to do is just do a quick check for the small angle approximation. Make sure we're using it correctly. All right. So I'm just going to do kind of a side note over here. Small angle check. Okay. So the only thing I need to do with make sure at the small angle is just do an inverse tangent. So I'll say that theta is tangent inverse, and I'm just going to do opposite over adjacent. So that's just going to be y over d, or over r. All right, so y over r. Okay, and so when I do that, I get so tangent theta. My y is the 6.2 millimeters I just got. My r is 1.24 meters. All right, and so I get, make sure I'm in degree mode. I think I am. Yeah. Oh yeah. So I get a fifth of a degree. Right. So very, very tiny. So about, actually more like a fourth, but 0.28 degrees. So oh yeah, we are good. We're well less than 15 degrees. Okay. All right. So we are safe to make the small angle approximation. So what's going to be different though with the liquid, right? How does the liquid change things? Okay. So let's do that. And then I actually have one more thing I want to say about air, but let's go to the liquid. So with the liquid, the spacing, okay, so the Maxima spacing, that's again the spacing between maxima, not the maximum spacing between something else, right? It's the spacing of maxima. All right. In that case, it's going to be r and then lambda, but lambda n, right? What's the n here? Is that another counting number? No, that's the index of refraction, right? That's from last week, right? Or the week before spring break. So the idea is that when when light travels through a different transparent medium other than a vacuum or air, effectively a vacuum, then that different medium slows down the light, increases the wavelength because it doesn't change the frequency by conservation of energy, but it changes the wavelength, and in changing the wavelength, it's going to make it, well, in this case, shorter. All right, so it's going to have a shorter wavelength. Okay, so then that's just times d. Okay, and so then lambda n is just going to be lambda over the index of refraction. So then we'd have our 1.24 meters. We'll have our 450 times 10 to the negative 9 meters, but divided by 1.73, the index of refraction. All right, and then that's all still going to be over the spacing of 90 microns. So 90 times 10 to the negative 6 meters. Okay, and so then that's going to give us a spacing of bright spots of, let's see, so the difference is instead of 450, it's going to be 450 divided by 1.73, which ends up being 260, right? So indeed, it's shorter, all right? And in fact, it goes, it becomes an invisible light, right? Because essentially it goes from being, at 450 nanometers we can see it, at 260 we can't see it, right? That's light with too short of a wavelength. Okay. So then 260. All right. And so that all looks good. So then the spacing is 2.38 times 10 to the negative 5. Okay. So now the fringes are so close together that they, if you could see them with, with the right lens or something, it would basically look like a band, right? Because they become much, much closer together. It'd be hard to distinguish them as individual bright spots. All right. But then the question is, how many more fit? Well, how many total bright spots fit on a screen that is, in this case, 55 centimeters across? Well, we have to take the overall size of the screen and then, basically divide it by the distance between spacing, right? Because that's going to tell us that how many bright spots fit. Okay. So let's see. So if we then take our, so I could find the so I could find the highest order M that fits, right? So here, what I did here is I found the spacing between any two ones. So I think that's a good idea, because we could just take the overall spacing of the screen, just divide, and then round. We would round down, because that would be the number of individual ones that fit. So then we'll have, number of what I call them here, fringes, bands, right? Interchangeable terms, fringes. So number of fringes is then just going to equal the overall length, we'll call that y total, divided by ym. Okay, so that's going to be our 55 centimeters divided by our spacing of 6.2 millimeters. Okay, so that's the total number of bright spots that fit, and we're going to round down, okay, because we have to get an integer number because you can't have a half bright spot. Okay, not for our purposes at least. Okay, so we'll take 0.55 and divide it by 0.0062. All right, so I have 88 that fit in this case. All right, so 88. In this case, with the liquid, well, we should have a lot more that fit, right? So that's the thing, as you go into a higher index of refraction, notice the trend here. The higher index of refraction means that you have a much more tightly spaced pattern of bright spots and dark spots. So that's always the case. As you go from air to any higher index of refraction, your pattern of interference, your interference pattern becomes much more tightly spaced. And we did a pretty big increase. Going to 1.73 is pretty high, right? I mean, think about water is only 1.33. Okay, so let's then take this results. So here we're simply going to have the same thing. So it's going to be 0.55, very similar, meters. Here I wrote centimeters, but I meant to say meters. Okay, and then we'll divide by our very close spacing number, 38 times 10 to the negative 5 meters. All right, so 0.55 divided by that one there. So there we have 230,000 of them that fit. Okay, so 230,000 fringes. Okay, so huge difference, right? Because we went up by two orders of magnitude difference, and so then we have a much bigger number that that fits in there. Okay, it's such a striking result. Yeah. Wow. Neat. Okay. So there you have it. Going from -3 to -5. Yeah. I mean, I guess it is kind of, I guess, because we're basically on the order of 1,000, and then we have a difference of, yeah, just the way it worked out. Like I'd expect it to maybe go up to like 10,000 or something, but not 230. But the numbers don't lie. Okay, so 230,000. That's our total number of bright spots, small angle approximation, and all of that. Okay, so please join me for part